Hi everyone, I'm Edwin, and my research project will be on CentOS. The main topics that I'll be talking about today will be process management, memory management, and file management. So here's the video I found during my research. Is it pronounced CentOS or is it pronounced CentOS?
And there was this guy that lives in the UK, and what he did was he was the first person to mention CentOS. He came up with the name CentOS. And it's funny because I said, I love CentOS. I love the name. I hate CentOS. I love CentOS, hate CentOS. And he goes, everybody said, why do you hate CentOS? And I said, because it's free. And 1 cent, which is what it's implying, is an infinite amount more money than free. And I said, I don't like it. It's emphasizing the wrong thing. And I said, but I do like CentOS. I said, you could type it however you want, but I just like CentOS. And of course, what took off? CentOS. But
So I thought that was pretty interesting. So what is CentOS? CentOS Linux distribution is a stable, predictable, manageable, and reproducible platform derived from the sources of Red Hat Enterprise Linux. So this was taken from their website, CentOS.org. So it stands for Community Enterprise Operating System. It is free to use. It is a community-supported platform, functionally compatible with the upstream source, Red Hat Enterprise Linux. So Greg Kurtzer, in the previous slide, founded the Chaos Linux project initially, and this eventually turned into the CentOS project in 2002. So in 2014, they've actually officially joined up with Red Hat while staying independent. So what is CentOS used for? It's actually one of the most popular Linux distro for web servers at the moment. So from my research, around 30% of all Linux web servers actually run this OS. So why is this the case? So it is an enterprise quality operating system first and foremost. It's based on something that's been examined, and it's a stabilized source code of Red Hat Enterprise. So what this means is that it is very stable. And of course, it is best of both worlds since it is also free. It does strive to maintain 100% compatibility with the upstream source, Red Hat Enterprise Linux. The only catch is that you don't get any of the commercial support. However, because it is community driven and supported, should usually find a lot of resources online. So here's a quick kernel overview. CentOS version 8 uses the Linux kernel 4.18. It is composed of 5 major subsystems. We have the process scheduler, the memory manager, virtual file system, network interface, and the inter-process communication interface. So we'll go ahead and talk about the first major topic, which will be process management. Here's a brief overview of the responsibilities of a process scheduler. It is what determines which process will have CPU execution time. It allows processes to fork new copies of themselves, receives interrupts and routes them to the appropriate kernel subsystem, manages the timer hardware, and cleans up process resources when they're done executing. So here in this diagram, you'll see that a lot of these other subsystems actually depend on the process scheduler, so it's quite important. So for CPU scheduling, for my research, there are 2 classes of processes. One's called real-time, and then the other is normal. So real-time processes are different in that they have strict scheduling requirements. They have to run for a specific amount of time without interruptions, otherwise their function will be damaged. So normal processes are scheduled after all real-time processes have been scheduled and executed, since normal processes do have a lower priority. Different scheduling policies exist for both real-time and normal processes, so we'll have a look at both of these today. Real-time processes use static priorities, while normal processes use dynamic priorities. So this is done through virtual runtime and something called niceness values, which we'll also discuss today. All scheduling is preemptive based on priorities. So we'll talk about what process priorities are and what niceness values are. So priority value is a process's actual priority level, which is used by the Linux kernel to schedule a task. So process priorities (PR) they range from 0 to 139. So 0 with the lower number being the most prioritized process, while a higher number, 139, is the lowest priority. So the way these are divided is that 0 to 99 is for real-time processes, while 100 to 139 are for normal processes. Nice values is a number that exists for user is a user space value that exists to change and can be thought of as like a modifier to change the priority of a process. Nice values range from -20 to 19, and then it maps to 100 to 139 for the user processes. So if 0, as we recall, is the highest priority, if we modify this priority level using the nice value of -20, it will actually increase the priority of that process. So what this means is the lower the nice value, the more priority it has. So -20 would mean the more priority it has, and opposite is the higher the nice value. If it's 19, then you're giving it a modifier of 19 on the original priority level, which for normal processes, this priority level becomes PR equals 20 plus the niceness value. So this is used for normal processes only. So the highest priority of a normal process, niceness value of -20. So you'll see that this is still lower than any real-time processes, since the real-time processes is 100 to 139. So we'll talk about real-time policies here. So there are two scheduling policies for real-time processes. First one is a first in, first out algorithm, and then the second one is the round robin. So first in, first out, process will continue to run until it yields the CPU, blocks itself, or it's preempted by another higher priority real-time process. There's no quantum, which means it can actually run indefinitely. So this will actually even block I/O processes that such as keyboard and mouse. So which is why real-time policies are not used for normal processes, because it's quite important to make sure we can still have I/O and can control the system. Round robin scheduling algorithm is identical to the first in, first out, except that each process can only run until it uses up a predetermined quantum, and if it does need rescheduling, then it just gets put into the back of the queue. So both of these real-time policies implement static priorities. So next we have normal policies. So normal policies include the scheduling other, scheduling batch, and scheduling idle. We'll be mostly focusing on scheduling other, since these other two are for lower priority processes and are usually of limited interest. And so the first one, scheduling other, is the default scheduling policy for normal processes. So this policy establishes a dynamic priority list, and this is based partly on the niceness value that we talked about in the previous slide. And this completely fair scheduling, CFS, is the current default process scheduler, and this was merged into the Linux 2.6 kernel since October 2007. So prior to this, the O of 1 scheduler was used. So we'll briefly just look at O of 1 scheduler, so then we can see how CFS improves from that. So the O of 1 scheduler can schedule processes within a constant amount of time. So this is why it's called the O of 1 scheduler. It follows the classical preemptive scheduling model, has fixed quantums and also explicit priority levels. Includes multiple scheduling queues, so you do have one per process priority. And data structures used to achieve the O of 1 include the run queues and priority arrays. The main issue with this older scheduler is that it uses complex heuristics used to mark if a process is I/O bound or CPU bound. So this is not optimal since it analyzes how much a process sleeps and then determines if that is an I/O bound or CPU bound process. And a I/O bound process then is given a bonus versus a CPU bound process is penalized. So, from the author of the CFS scheduler, Ingo Molnar, he says that CFS basically models an ideal precise multitasking CPU on real hardware. So what this means is that it tries to enforce a optimal fairness to all the processes when we schedule them. So we'll have a look at what CFS does. So the main advantage and the improvement over the O of 1 scheduler is that no complex heuristics are used, such as fixed quantums or explicit priorities or the bonus or penalties that I had mentioned. So the goal of this scheduler is to divide the CPU time fairly or equally amongst the processes, as the name would suggest. It has an elegant handling and balancing of I/O and CPU bound processes, which we'll see in the upcoming slides. CPU execution time given to these normal processes, they're determined dynamically, and this is based on the number of processes ready to be scheduled. So there's a concept for the CFS scheduler. It's called the target latency. We can think of this TL. We can think of this as like a block of time, which is the minimum amount of time required for every runnable task to get a turn for CPU execution time. So we will have a look at what optimal fairness means and how CFS implements this idea. So the default target latency is approximately 20 milliseconds. This is the period in which all run queue tasks are scheduled at least once. So ideal fairness is the idea that each runnable process should get 1 out of n slice of this target latency, where n is the number of runnable processes available to be scheduled. So for example, if there are 5 processes, each process should then get 1/5 slice of the TL, which is 4 milliseconds. And another example is if there's only one process ready for CPU time, then that lucky process would get one out of one slice of the target latency, which is the full 20 milliseconds. So do note also the nice values per process. It further modifies this 1 out of n slice. That represents fairness amongst all the runnable processes, and this is how we can kind of enforce the priority levels. So let's just go through an example where we have n is equal to 4 and the target latency is 8 milliseconds. So we'll also assume that all these processes have a same nice value, so they have equal weights. We'll assume no new processes arrive. And so yeah, the example is each process would then get 1 out of n. In this example, we have 4 processes, which means each one will get 25% of the CPU time. So here you'll see the burst time that's required for each of the processes to finish executing. Here's a timeline of how each of the TL is broken down. So you see that it is, we try to give each process a fair share of the time. So 2 seconds, 2 seconds, 2 seconds, 2 seconds. And this makes up for the 8 milliseconds of the target latency. And this will go until process 1 and process 3 finishes at 8 milliseconds. So you see this adds up to 8 and this also adds up to 8. So after this point, then the number of processes left becomes 2. So then each process will get 50% of the CPU time. And because TL is 8, then each of the process 2 and process 4 would have 4 milliseconds to execute. And then you'll see that once process 2 is complete, then process 4 will have the full 8 milliseconds to itself. So here's a Gantt chart that I created. This basically shows what happens from the previous slide. So we have the 4 processes being equally distributed and shared in one TL, and then this goes until they all finish, and then process 2 and process 4 would each share half of the target latency, and then finally we'll have process 4 having the full 8 seconds to itself. We'll talk about what dynamic priorities are, since this is used only in the user process or normal process. So each ready process has a virtual runtime, so it's called the V runtime, and this is used along with the nice values to implement this dynamic priorities. So if a process has a low V runtime, then it has a higher priority. Because if a process hasn't gotten execution time, then we do want to prioritize that. And then likewise, if a process has already gotten execution time, then it will have a high virtual runtime assigned to it. What this means is that it then has a lower priority. So this is the way that processes are scheduled. They're based on the priorities and the virtual runtime. And the way that it is updated is virtual runtime plus the time multiplied by the weight based on the nice value of the process. So the nice value here will increase the weight of the time, which means that lower priority processes actually will have basically time moving faster, which will lower them on the priority list. So once again, a higher nice value means a lower priority, and this is how it's implemented using this formula here. So this solves the issue where I/O processes may be starved, since I/O processes sleep for a long time, and this means their virtual runtime will be low, and they will have a higher priority when they are unblocked. So this really helps where we want a lot of I/O and Swift interactions, and this is how it elegantly implements the solution. So we'll talk about CFS implementation as well. So it uses a red-black tree where each node represents a process. These nodes are ordered based on their virtual runtime. So you'll see that here's a self-balancing binary search tree, and the nodes on the left have lower virtual runtime than the nodes on the right. So this is efficient because we can quickly get the lowest virtual runtime node, which is always going to be on the leftmost node. And it's self-balancing, which means that no path in the tree is twice as long as any other path. And this data structure is used because it is very efficient. As we may recall, the binary search tree has a time complexity of O log n for insertion and deletion. So we'll also see that as processes are finished, and if they need to be rescheduled again, their virtual runtime will be updated, and which means processes that needs to get rescheduled will move from the left to the right of the tree, and then of course the priority levels for the right of the tree will also start to migrate to the left as tasks are completed. So we'll talk a little bit about context switches. So do recall from our lectures that context switches they can be expensive. So if let's say there is a minimum of 1 milliseconds for every context switch, then having too many processes and too many context switches can be quite detrimental. So the way that CFS handles this is a concept of minimum granularity for each of the processes. So what this means is that for any process, there is a minimum amount of time that this process must run before being preempted. So what this does is it prevents incurring a large overhead if there's too many processes, and makes sure that it does run for the minimum granularity time. The scheduler then would only reschedule based on the scheduling period. And this is determined if the target latency is 20 milliseconds and the minimum granularity is 4 milliseconds, then this also means 20 divided by 4 is we would have 5 processes. So 5 processes or fewer would allow each process a turn during the target latency. And likewise, the scheduling period can be determined by multiplying the number of processes that we have to schedule with the minimum granularity, which is 4 times 10, so we know that we can reschedule every 40 milliseconds. So if there are too many processes that we need to schedule, then fairness just goes out the window, and this is also how we can prevent that by changing the scheduling period. The next topic we'll go over is memory management. So here's a quick overview of what Memory Manager in Linux can do for us. Provides us with a large address space. This is what allows the OS to use a larger amount of memory than it actually has in physical RAM. It offers us protection because we want every process to have its own virtual address space. This is important because this way the code and the data are protected from rogue programs. And memory mapping. Contents of a file are linked directly into the virtual address space of a process. Also provides us with fair physical memory allocation and also shared virtual memory. It allows processes to share memory for more efficient use. So an example of this would be a system running the bash command shell. So rather than having several copies of bash, one in each process's virtual address space, it is more efficient, better to just have one copy in physical memory, and all of the processes running bash share this one. So we'll talk a little bit about virtual memory. So Linux does use virtual memory as discussed in our lectures. All addresses are virtual addresses, and these are converted to physical space, as we know, by the memory management unit. Pages are used. So virtual addresses are divided into small size chunks. Most systems use 4 KB page sizes. The TLB, as we know, holds entries of the mapping virtual addresses. It's got the physical address and also the permissions bits. Each process can have different memory mapping. And then we have shared memory is easily implemented with the MMU. All right, here's some concepts that we have already covered in class, so I'll just quickly go through them. So this is the virtual to the physical address mapping. It's done with page tables, as we know. So in the page model, virtual addresses, they're composed of the two parts, the offset and the page frame number, the base. So virtual memory can be mapped into the physical pages in any order. I guess they're called frames in the physical memory. And physical memory does not have to be contiguous. So each process would have its own separate page table, and this is the way that it can share the physical memory. So in this example, we actually have 2 processes, each with their own page tables, and then as you can see here, in this page index, they both end up referring to the same physical frame. So once again, different pages can reference the same physical page frame number. So in Linux, it does use demand paging as opposed to loading all the pages. This is also known as lazy loading. So and this is only brought in, so pages are only brought in into memory from hard disk if the execution process actually needs them. So page table uses a bit to mark if this page is valid or invalid in the table, and valid pages refer to one that's currently in main memory, and invalid pages cause page faults, as we know. It allows efficient use of physical memory, since page faults are used to determine which parts of the image to bring into memory for execution. So the more processes can be loaded, and this reduces context switching time, which is one of the major advantages of demand paging. So we'll talk about page implementation and how that's done. So all physical pages in the system, they're described by a data structure called memmap, and this is an array of memmap t. So memmap t can be thought of as a structure that holds the count, age, and the physical page number. So it's a good representation of the physical page frame number. So the count is telling you if it's shared amongst other users, so the number of processes that share it. Age of the page is used to determine if it's a good candidate for swapping, as we'll see in the upcoming slide. And once again, map nr is the physical page frame number. So free area is an array used by the page allocation code to find and free pages. The first element describes single pages, and then the second element describes 2 pages, the third element 4 pages, and so on. So this increases in powers of 2, and we'll see that in the next slide here. So here is an example where we have the free area data structure. So we can look at this as a list where the first element represents pages that are in blocks of 1, and then in the next one we would have 2, and then in the next one we would have 4, and so on. So this is used as a queue ahead and has pointers to them, to the memmap t in the memmap array. So we'll have a look here as well. So we'll see that this data structure is what allows us to track map what's been allocated and deallocated in terms of memory. Very similar to the memory manager lab that we've done, but this is how it's implemented. And then of course it has a doubly linked list to all the actual blocks of memories. So map is a pointer to a bitmap, and as I mentioned, this tracks the allocated groups of pages of the same size. So once again, here's the diagram. So page allocation. So Linux uses the buddy algorithm to allocate and deallocate blocks of pages. So what it does is it first attempts to allocate blocks of 1 or more physical frames that are in powers of 2. So it first checks that there are enough free frames in the system, and then it will search the free area data structure for a block of pages of the size requested. So if, let's say, for this example, we request a size of 4, then we would go down this list for the free area data structure. And then in the first one, we know that it wouldn't be here because this represents one page block. And then in the next one, we know that this one's going to be 2, and then we won't find that in there either. So that means that we'll have to go into index 2 to find a block of 4. So yeah, each element of the free area has the bitmap of the allocated blocks. So this map is how we can track where these blocks are, the free blocks are. So if no blocks of the requests are free, so as I demonstrated here, then it just moves up the list in powers of 2, and then continues to search until a block size is found. So if we do end up finding a block size larger than what we requested, then we can just basically break it down. So if we requested a block size of 2 and this block size is 4 at the index of 2, then what we can do is basically break down this free block into 2 and 2, and this would prevent internal fragmentation, which means we can reuse this block of 2. So then this new free block of 2 would be inserted into index 1, since index 1 is what tracks blocks of 2. Yeah, so free blocks will be queued into the appropriate index. In terms of page deallocation, as we have seen, so allocating blocks leads to fragmented memory. With the larger blocks of free frames, they get broken down into the smaller ones, and then they get basically recycled and re-put back into the smaller queues. Deallocation then recombines these pages back into the larger blocks as possible. Very similar to the memory manager lab we did, combining these blocks. Since we do want larger blocks, since we have more flexibility with them, since if we ever need to, we can just simply break them down again. So every time a block is free, then the adjacent buddy block of the same size checks to see if it's free. If it is, then it is recombined, and then it continues to recombine until it can. And the last thing we'll talk about for memory manager, memory management, is swapping. So swapping from disk into memory of pages needs to be done if there's not enough physical memory to load these pages. So the OS has to decide, well, which page does it swap out or discard from physical memory. So in Linux, it uses the least recently used LRU page swapping algorithm. So this is the one we talked about in the lecture. So the more that a page is used, then of course the younger it is. The least that it is used, the older and the more stale it becomes. So this is tracked by the page data structure right here. Age is used to determine if it's a good candidate for swapping. All right, and finally, we'll talk about the last topic, which is the file system. So here's a overview of the Linux file system. So in Linux, everything is treated as a file. So the file system can be thought of as like a tree-like structure. You can see here we have a diagram of what this may look like. So it starts at the root, and this is indicated by the /. So this is what is known as the root directory. So it contains all these underlying files and directories, and it does also use the absolute relative paths that we've talked about. So to go one directory below, we just simply use the /, and then if we want to go back up one directory, the 2 dots is used. Here we have directories in the Linux system. So these are different than the usual Windows directories. So here are some of the ones that I've personally had to go into and use for my work. And the first one is /bin. This is where common programs are located, shared by the system and the users. And then we have /boot. This is for the startup files and the kernel, VM, Linux. /etc. This is where we can find a lot of system configuration files. /home. This is equivalent to like the Windows home directory. Is where you would go if you did like a /tilde, which is the equivalent of the /home. /root is the root user, which is the admin user's home directory. Temporary space is the /tmp. So a lot of times if we don't have, if you want to transfer stuff between user spaces, you can put them into /tmp. And then finally /var. This is where you can find a lot of variable files. I personally used it to find system log files. So we'll just briefly talk about the file structure. So a file is represented by an inode. So it contains information about the actual data that makes up the file. So this includes things like which user it belongs to and where it is actually located on the hard disk. It describes the data structure on the hard disk, and file names in Linux are case sensitive, and they can contain any characters other than 1 and the /. Use of the file extensions is not required, although it is generally used just to know what kind of file it is, just by looking at the name. Directories are treated like normal files, and we'll see that in the next slide. So inode. So we'll go into a little more details about inode. Inode is a data structure. They point to blocks that make up what we call a file. So here this diagram has an example of music.mp3. It has the inode, which is a unique number. As we can see, there's a lot of metadata about the file. And then it also has pointers that will point to the actual file contents. So located near the beginning of a partition, it stores all the information, the metadata. This is except for the file name and the actual data. So when we reference the inode number, we can retrieve the metadata about the file. Inode number is unique, and it has to be unique, and it has the following attributes such as size, owner, date, time, permissions, the access control, the file type, number of links, and of course additional metadata. We can actually check a list of inode numbers in the terminal using the command, let's say ls, to list the files, and then with the -i flag. So when we create a new file in Linux, it is assigned a file name and also the inode number. So both are stored as an entry in the directory. So if we do run out of inode numbers, then we do run out of space in our file system, even if there's enough free space on the disks. A file system is basically just a link to this inode number. So if we create a hard link, it just creates another file with a link to the same underlying inode. So when we delete a file, it removes one of the links to the inode, and inodes are only deleted when all these links have been deleted. So this is one major reason why you'll hear that Linux systems don't require system reboots when you install a lot of software, and this is one of the reasons why. So here are just some of the system calls that are associated with files. So here we have some for file operations. We have things from renaming the file, closing the file, and we've used some of these in our labs. And here are some directory operations. We can create a directory, we can delete a directory, and then of course we can change the working directory. Here are some system calls for link operations. So we can create a hard link to a file, we can create the symbolic link to a file, and then of course we can delete a name, and we can also read the value of a symbolic link. That concludes my presentation. Thank you for listening, and I hope you learned something.